Thank you for joining this webinar. I'm Travis Waineo, the Senior R&D Manager for Energy Storage at ANA, and today we're going to get into hybrid power generation design. A quick summary of this webinar: we're going to discuss why we need hybrid power in the first place. We're going to go into types of systems out there already today. We're going to get into some existing hybrid applications from other industries and how we can apply it to hybrid power generation. Then we're going to get into some design objectives for hybrid systems and how it applies to power generation. We're going to touch on battery chemistry, and then we're going to get into incident energy and arc flash ratings of hybrid systems. We'll go a little bit into parallel scalability and hybrid versatility. And then we're going to touch on the economics of hybrids, where it makes sense and where it doesn't. And then we're going to go through a case study for a hybrid system that was completed recently on an ANA EBOS product. So the first question that comes to mind is, why hybrid power? Why do we need to change things? And the main reason why we want to explore hybrid power is we want that generator running less. So when it's running, we want it to be running at its most efficient point. Otherwise, we want it turned off. That's going to result in reduced fuel costs. In a lot of applications, we see up to 75% less fuel cost than when you compare it to a standard generator. We're also looking at a longer component life. So a standard generator, when it's running at 1800 RPM to generate the 60 hertz frequency, has to be running at all times, no matter the load. And that means that any time it's running, you're going to be adding wear and tear on the engine. When you have a hybrid system, that engine is now running only at its most efficient point, and otherwise it's turned off. And essentially that results in high efficiency of the hybrid system because we're optimizing the generator to run at its most efficient point. Let's get a little bit into the two types of systems out there today. There's an AC coupled diesel generator and BESS, which means the generator powers both the load and the battery. So when the load is light, the battery attempts to charge to bring the load up on the diesel generator. And when the battery is full, the diesel generator turns off and the battery powers the load directly. It requires some synchronization between the two systems, but this is one of the AC coupled is one of the types of systems out there today. The other type is a DC coupled system, which means that the battery is always powering the load. The stored energy in the battery is always feeding the load, and when the battery state of charge drops low, it turns the generator on, which charges the battery. At no point in a DC coupled hybrid system does the generator power the load. And we'll get into incident energy and how that is affected by this later on. So looking at an automotive hybrid, there's a lot of parallels that can be made between automotive and the power generation industry. If we look at the F-150, for example, there's a multiple models of the F-150 available. The standard F-150, which has a 3.5 liter EcoBoost engine, it's about 300 kilowatts. You've got the PowerBoost hybrid, and you've got the F-150 Lightning battery electric vehicle, or BEV. In all of these systems, the engine size or the power output capability is about the same, but the fuel efficiency on the standard F-150 is 18 miles per gallon city, 24 miles per gallon highway. When you go to the PowerBoost system, you get an improved efficiency of 25 miles per gallon city and 26 highway. And they have an MPG equivalent for the Lightning BEV, but it's hard to compare that to some of the other systems because we don't have a really good comparison in our mind. When you look at the refuel time, for a standard F-150, it's about 4.3 minutes to refuel it from empty to full. with a standard gas pump. The total range on that is about 624 miles. And when you step up to the e-Boost hybrid, the PowerBoost hybrid, you've got a refuel time of the same amount, but the total range bumps up to about 750 miles due to the increased efficiency. On the F-150 Lightning, because it's a battery only, the charge time at max charge rate is about 38 minutes, and that results in a total range of about 320 miles. The main limitation on that mileage is the battery size for the Power Lightning BEV. Now, we could build a hypothetical F-150, standard F-150, and a Lightning BEV, and that would result in a pretty inefficient package from a packaging perspective, but you could get the same efficiency as that PowerBoost hybrid, and you would have a significantly long period of runtime on that Lightning battery when it's running, but it's not necessarily an optimized package for that system. Let's take that automotive hybrids and apply it to generators. So I took a standard 220 kVA generator, which has an output capability of about 176 kilowatts. And if you look at the fuel efficiency at a 10% load, you're getting about 4.4 kilowatt hours per gallon. And at 90% load, that generator is really efficient at 14 kilowatt hours per gallon. The same refuel time it's about 5.7 minutes for that generator, and the total runtime is 71 hours at a 10% load. I selected a 10% load because across the industry in rental power generation, we've looked at thousands of units, and the average load on those units, over 3,000 units, was 10%. So I'm using that as the baseline calculation for this. When we step up to the 220 kVA hybrid, in this case there's a 125 kVA generator paired with it. The fuel efficiency at 10% load goes up to about 13.5 kilowatt hours per gallon, and it's about the same at 90% load. In this case, the battery size is 75 kilowatt hours, and the refuel time is about 3.3 minutes because it's a smaller generator paired with that system. And that, at a 10% load, that gives you a total runtime of about 129 hours. Now we can do a comparison to a 250 kVA BESS, which is about 200 kW output capability. And on that one, the battery size, there's systems out there where the battery size is 575 kilowatt hours. With that system, the refuel time or the recharge time is about 172 minutes. It's a little bit over 2 hours at the max charge rate, and that results in a runtime of, at a 10% load, 32 hours. So we could take that same BESS and pair it with a 220 kVA generator and come up with something that's a very similar efficiency to the 220 kVA hybrid we talked about, but it's got a big battery and it's got a longer, it's not necessarily an optimized system for the overall hybrid. When you have a standard generator there, you get a runtime of about 161 hours, but it's a much larger package size than the hybrid we explained just a second ago. So when we take a fresh, clean sheet of paper and look at a hybrid system design, we have a few objectives in front of us. The main one is we want to prevent generator wet stacking. Tier 4 engines are notoriously known for wet stacking, especially when you're running them at light load. And we just discussed about the average load in our industry being 10%. So we want to prevent wet stacking. The way to do that is we want the generator running for at least 30 minutes at about a 60% or greater load. We also want to maximize the generator efficiency. So we want to eliminate the light load inefficiency we talked about previously. When the generator is at 90% load, it's generating a really high efficiency, 14 kilowatt hours per gallon of diesel. At 10% load, that drops way down to 4.4 kilowatt hours per gallon. So we want to use hybrid to maximize that efficiency. We want to use the existing service and refueling network. So if there's a system out there already, a diesel truck out there on a job site, fueling other equipment, we want to make sure we can utilize that same diesel fuel for the hybrid system. We want the same operational conditions as a generator. So if a generator can run, at negative 30 C out in the, way up north, we want the hybrid system to be able to do the same thing. And it's the same thing in the desert in the middle of summer. We want to be able to operate in the same conditions. That allows anybody to know that they can trust that hybrid system when they put it on a job site, regardless of where it is. We also want the hybrid system to last as long as a generator. Our customers are already used to the life of a generator and how long those run. We want the hybrid system to also work in that same capacity. The other little known capability is we want the hybrid system to also be able to start the same equipment that a generator could use. We want, regardless of the generator state, so if you have a paired generator with your hybrid on your battery, we want that battery to be able to start anything that a standard generator could start. And that's regardless of the generator state. So if the generator's off, we still have to be able to start the same equipment, a pump or something downstream that a generator could normally start. So going through, you can start by selecting battery chemistries. And there's 3 primary battery chemistries in the industry today. The first one we'll discuss is NMC. Nickel, manganese, cobalt is it's a very energy dense chemistry, and it is pretty well known in the automotive industry for energy density because in the battery electric vehicle space they need to have a lot of that energy density. So NMC has been a pretty high choice for those. There can be issues with thermal runaway, but that can be mitigated by building systems around that chemistry to prevent thermal runaway. At the cell level, there's risk, but it can be mitigated at the system level. LFP has really gained in popularity. It's another relatively energy-dense source, and it's typically lower cost per kilowatt hour than NMC, and it has a slightly higher lifetime capability in terms of charge and discharge cycles. The slightly lower energy density is offset by the lower cost, so you can typically get a pretty high amount of energy storage for a low cost with LFP. And it's really increased adoption in automotive and energy storage applications where you really want that energy density to be able to store charge from the grid or from a generator or something else on site. Then we can get into LTO. So LTO has a very high power density. The energy density is not quite as high as the other systems, but because of the power density, and we'll get into how to design a system with LTO compared to the other types of battery chemistries, but it's inherently a safer battery chemistry. It does not go into thermal runaway due to mechanical damage, and it's much more stable due to the titanate anode inside of that chemistry. So LTO is a really good choice for hybrid energy applications because of the high cycle life and the inherent safety of the chemistry and the overall power density of the battery. Going into battery capacity, one of the common misnomers is the battery runtime equates to output efficiency or generator hybrid system efficiency. And the actuality is the number of generator run hours at the efficiency of the generator is what drives the efficiency of the hybrid system. So in LTO's case, typically the battery size is much smaller than with LFP and NMC, and we'll get into that in a little bit. But because you can reduce the battery size with LTO, the generator runtime on the same application with the same load ends up being the same. So your efficiency is very, very similar between LTO and LFP or NMC in an energy storage application where you're connected to a diesel generator. So just going through the LTO and comparing it to the NMC and LFP chemistry, if you run this same scenario at a 10% load, the battery C rate limit is what determines the battery size. So if this is a 70 kVA application, if you have a 65 or 70 kVA generator paired with a battery, when you use an LTO battery, you can design that system to be about 23 kilowatt hours of energy storage. That meets all of the parameters above where we talked about the generator running for 30 minutes at least 60% load and staying inside of the maximum capability of that battery. When you go to LFP and NMC, typically you want to keep the battery C rate under 1C. In this case, I designed it for a half C. On that system, we would have to be about 93 kilowatt hours of battery for that application, which results in a lot more battery that you have to have on the site for the same system. And it also results in a larger package when you have that much more battery. So overall, you can design systems with both LFP, NMC, or LTO. It's just how you design the system and how you size the battery capacity to match for the application. We talked a little bit about on the DC coupled system, the inverter drives the load directly. So since the load is only powered from the battery on a DC coupled system, the generator is isolated from the load. Generators are notoriously high for incident energy. If you look on the right, on the curve here on the graph, you can see the fault curve for a typical generator and compare it to an inverter driven system. So when you're AC coupled with the generator, your fault curve is going to match the generator. But when you're DC coupled, like on the lower right side, your inverter is going to be able to detect and fault out when there's a fault in the downstream system. Essentially what that means is we can reduce the amount of incident energy when you're on a DC coupled system because the inverter will catch a fault so much faster than a standard generator or an AC coupled hybrid system would. So we're going through the testing at the time, but we think we can get the incident energy below the 1.2 cal per centimeter squared threshold for OSHA PPE requirements. So parallel scalability. With hybrid systems, by using multiple units, you can build up your capability. You can also do that with generators, but it's become a lot easier with especially DC coupled hybrid systems where you can basically put as many of these systems on a site as needed and you can build up the power node. So you could take a 70 kVA building block and build up, through a number of those around. You can build up enough of those to get the power that your load needs. And then when that job is done, you can break that system down into the small 70 kVA building blocks and put it on, multiple job sites. So that's really where the parallel scalability has become important in hybrid systems, is just the versatility of building up the power nodes that you need for that job and then changing it for the next job by using a number of smaller nodes rather than more larger ones. So hybrid versatility. Hybrids, we have found, are really an ideal power generation solution for a variety of industries. Very useful in construction. We're going to get into a construction site case study in a little bit that was run on a guard shack on a construction site for about a year. It's also very useful in manufacturing, film and TV, utilities. We've found applications in the commercial space and municipalities, hospitals, and even disaster relief. So getting into the economics of a hybrid system, this is a theoretical 5-year cost of equipment for a standard diesel generator versus a hybrid system. So in this case, we've got a 70 kVA hybrid, and we're comparing it to a 70 kVA generator. There's a capital investment. In this case, the capital investment is higher on the hybrid generator, $170,000 versus $50,000. But when you run this again at that 10% load that we talked about earlier, the electrical load hours on the hybrid system and the generator are the same. And this is a 2-shift per day on a 5-year period. You're going to get 20,800 hours on the hybrid system and the generator. But when you compare the generator run hours, on the hybrid system, you're around 4,600 hours versus 20,800 on a standard generator. So you've really reduced the amount of hours on the generator in this application. The fuel burn comparison for the life of this system for that 5-year study is 17,000 gallons versus 36,000 gallons. So your total fuel bill is significantly less. And then when you look at the residual value of that equipment after the 5 years, that generator only has 4,600 hours on it. So the residual value, the resale value of that equipment is going to be worth a lot more than it would with a standard generator with 20,000 hours on it. So the total cost of equipment over 5 years on a 2-shift application is significantly different when you compare a hybrid generator versus a standard diesel generator. And that's really where it makes a lot of sense, is when you can reduce your fuel bill and increase your equipment resale value or equipment life by using hybrid versus a standard diesel gen. So this is the case study that was run on a guard shack on a site for a year using a 25 kVA hybrid. So this was running 24/7, 365. And if you compare the hybrid runtime, the battery ran 8,390 hours. That's exactly the amount of time that a standard generator would have run as well. But in this case, the generator only ran, because it was a hybrid, the generator only ran 783 hours. So it's a 91% reduction in generator runtime for this application. And when you look at it, the hybrid fuel consumption was 1,076 gallons burned over that 1-year period, which is an 83% reduction in fuel burn versus a standard generator. And it also resulted in 15 fewer oil changes when you compared it to the standard generator application. And the emissions were reduced by 53 metric tons. This resulted in a financial impact of $15,000 per year of operational savings in fuel and maintenance, and the carbon reduction equivalent to 5 homes or 11 cars. The operational impact is that equipment, that generator has significantly less hours, so that whole system will run a much longer period of time than it would have if it had been a standard generator on that site. Not to mention the wet stacking concerns and other issues with a standard generator running at a very light load like that. And the job site impact is, in this case, there was LTO battery chemistry, which has no concern for thermal runaway in this application because it's inherently a safe chemistry because of that anode. So to summarize, why we would use hybrids is the reduced fuel cost, like we talked about. We see a significant reduction in fuel costs compared to a standard generator. The maintenance is reduced by a significant amount as well because that generator service interval is extended significantly. That also results in a longer generator life because when that generator is on, it's running at its most efficient point and putting out its maximum capability. Otherwise, it's turned off and everything is run off of the hybrid system. We designed the system to have significantly increased efficiency because that generator, again, is running at its most efficient point when it is turned on. All of this drills down into a lower total cost of ownership for this application and results in lower emissions, and because there's remote monitoring and safe battery chemistry, it's a significant improvement for the customer using this product as well. Thanks for joining this webinar. We're going to go through the Q&A next.
All right, thanks, Travis. So if you have any questions, feel free to drop them in the chat or in the Q&A, or if you want to raise your hand.
So far, so good. Looks like we have a raised hand.
Hand raised, yes. So I gave you permission to talk, so you should be able to unmute now.
Hello, so do you hear me?
Yes.
Yeah.
Okay, perfect. Well, thank you for the presentation and all the valuable information that you've shared with us in this webinar. I do have a question regarding the average load, because I see all the calculations or the let's say the base for the design of the system is pretty much on the 10% load. What in terms of the let's say the optimum average load that we need to look at while discussing with the customer to see that system is going to be much more beneficial for them in terms of the cost savings and as an economic solution for them.
Yeah, that's a great question. A standard generator above about 60% load is actually really, really efficient. So it really, in most cases, it doesn't make sense to put a battery out there or a hybrid system out there if your average load is above 60%. Now, we're a little bit unique in the rental industry in that people always oversize that generator. There's no penalty to oversize it. There are no immediate penalty to oversize it other than potentially wet stacking, but there's always a penalty if they undersize that generator. So naturally, everybody's going to try to overspec the gen, and that leads to that 10% number on average. But really, if you find an application that is 60% or greater on average load, it's most likely the best scenario to just put a standard generator out there. The other place where hybrids work is if you've got like your peak load is about 3 times your continuous. If that's a scenario, so for motor starting or other situations, if your peak load is about 3 times your continuous load, hybrid's a great choice for that, because essentially you have to oversize that generator quite a bit to handle the peak load. And that's another application where hybrid is really valuable. Does that answer your question?
Yes, it does. Thank you.
Yeah, thanks for asking it. Anyone else on here? And us have another one.
Yes, thank you for this. Just in terms of the battery and how it's actually it can handle the different kind of loads, like as you've already mentioned something which is really important about the motor loads as inductive one. And what about the harmonics? Like if the battery is gonna deal with some VFDs or maybe other battery chargers like for EV buses or something like that. So in terms of the design or something that we need to bear in mind, what are the your guide, let's say your guidance or guidelines on this kind of applications?
Yeah, harmonics on the output are very application or are very design dependent. So hopefully you can reach out to the manufacturer and get the harmonic information. In a DC coupled system, that's very easily available from the manufacturer. And yeah, they should have harmonics on a purely resistive load and some mixed power factor loads, right? In an AC coupled system where you might have a couple of assets on the AC system, it's a little bit harder to calculate harmonics because it's kind of a combination between the two units on the AC line. But that's something that's essentially you have to probably do on site. But when all of the AC output comes off of the one inverter or VFD, that's all designed originally into the first design, is making sure that all of the filtering on the output covers the harmonics or keeps the harmonics to a minimum. So for example, our system with the AC, or it's a DC coupled system, but there's a significant amount of filtering and LCL filter downstream of the VFD. And on average, the harmonics are about 0.5%. And that's just by design. We've really tried to keep the harmonics really, really clean, which in most cases, we're trying to match a standard generator in how we meet the harmonics. But in this system, it's quite a bit better than a standard generator across the board, just because it's VFD driven, and then there's a good filter on the output of it. You also asked a question about peak loading. So some systems out there, there's a couple of different ranges for peak load versus continuous when you look at a BESS, because you can't rely on that generator to be on to provide a peak load for motor starting or something else. So you have to size that BESS to be able to start the same gear that could be started from a standard generator. So an example is take maybe a 10-ton AC unit on a 70 kVA generator. That generator can provide 2 to 3 times that 70 kVA rating for motor starting. It won't do that continuously, but it'll do that for a short period to start the motor on that AC unit or the compressor. When you get into BESSes, sometimes they rate the inverter size to only basically match the continuous load. So you might have an inverter that's rated for 77 kVA on the output. And the other way that systems are sized, and this is what we've tried to do, is take whatever that motor starting rating is for a 70 kVA generator and match it for the hybrid system. So you don't care if the generator's on or off. None of that matters. We just want to make sure that if you can start a 10-ton AC unit with a 70 kVA gen, you will be able to start it with a 70 kVA hybrid system as well. So there's a couple of different philosophies around that. One is provide the hybrid system to handle kind of the peak load, the continuous load, but then the peak load has to be coupled with the generator. Or the other option is, let's just make sure whenever something starts, no matter the generator status, that the hybrid system will be able to start it.
Okay, thank you. Regarding the harmonics one, because my question is pretty much in terms of, okay, we have some kind of loads that's actually, they are the kind of load that they are a problem, because I think that's your inverter, it's you use the IGBT technology, which is the best in the market. But the problem is that that kind of system is gonna face some kind of loads where a very low, let's say, efficiency, or let's say performance, like there will be some kind of loads where 6 poles rectifiers are used, which gonna generate a lot of harmonics. So my question is pretty much in terms of how this system, or the battery, is gonna handle that kind of let's say harmonics generated by those loads.
Oh, okay. I That's probably a more application specific question. I was thinking maybe, if you had a 0.5 power factor or something, inverters will automatically compensate for that. But like a 6 pulse drive on the output, that's really where your filtering is important to make sure you're handling the harmonics, because those things are choppy. There's no question about it. So it's more, in that case, it's more about how do we mitigate it. Are you concerned about other equipment on the line in that case? Or is it just that 6 pulse is the only load on the output of that system?
Well, it's at the end of the day, it's gonna be a mix between, because we don't have, one customer with the one type of load, but there are a mix of kind of loads that's actually they usually have in their systems. And so just what we would like to be in a position to be aware of those issues, as well as, in the rental departments. We're not talking about a new project with a new equipment, with a new genset or new battery hybrid system. We need to offer this a solution that it's okay, it's gonna work, and for as well as we do not want to be in a situation that we are gonna harm our equipment as well. And for sure, for the customer side, we cannot just say to him, okay, it is 6 poles rectifier, so you need to add a lot of filtering over there, etc. So that's not, it's not gonna work. So for us, so we need to be considering these kind of issues, and see if, okay, for a normal genset, it's pretty much in terms of we can let's say handle this by oversizing the generator, but from the battery system, what we need to look at.
Yeah, I think you could probably reach out to me separately and we could discuss in more detail. I'd love to have that conversation around specifically what it is, but I think from just at a high level, we've designed the battery to hopefully take the same, if you would put a 70 kVA to run your 6 pulse drive down the line, I would feel pretty confident that a 70 kVA hybrid that we've developed would do the same thing. But I'd love to look into the specifics, because it sounds like you have some pretty specific use cases that we could investigate. So feel free to reach out, and I'd love to have a conversation with you.
Sure, thank you.
Mm-hmm.
Okay, it looks like we have a couple in the chat and then one more raised hand.
Yeah, so it looks like, will there be a copy of the slide deck shared? I think we can share that with you, yeah. Let's see, what battery chemistry, Kevin asks, what battery chemistry is best for cold weather operation? At the cell level, LTO has the lowest minimum operating temperature, so you can charge at negative 30 C, which is negative 14 Fahrenheit. LFP and NMC, you need to be above about 32 degrees. I think it's 0 C, which is 32 Fahrenheit in order to charge. That's at the cell level. So just like any battery chemistry, you can always add things at the system level to mitigate that cold weather issue with some of the chemistries. So you can add in a battery blanket or an enclosure heater to allow to fix some of the issues that you see with a standard battery. So automotive does that all the time. They add heaters around the battery. It's not as efficient because then you're burning energy to do that, but there's always trade-offs, right? So it's, do you start at the cell level with the lowest operating temperature, or do you start with a different, like the LFP or NMC, and then mitigate the low temperature limitations by adding some heaters? So, and then the limiting factor in the hybrid system for the minimum operating temperature is the battery. You nailed it. That's really the lone most difficult question for hybrid system design is, how do I mitigate battery limitations at cold temperature? So, thanks, Kevin. Looks like Joseph has a question.
Your case studies and information was particular to the rental market, portable stuff. What's the application for stationary hybrids?
Yeah, there's a couple of use cases where stationary is you have to look at it pretty specifically. Hybrids can be useful in stationary in that you can use it for, you can basically set up the hybrid to auto load bank for you, where you can drain your battery and then you just charge the battery with your gen, and that's doing your load bank testing. We haven't seen a ton of that, but that's one of the concepts for hybrids, is to basically use the battery to load bank the generator. And that could fulfill your requirement for running that generator every once in a while. And rather than having to put a load bank on it, you just put it into the battery. Around the case study and the efficiency and fuel savings, that one is most of the time on a standby application, because with the current hybrid system economics and your standard or your standby runtime, most of the time it doesn't make a lot of sense to have a hybrid system on a standby application, just because you're not getting that fuel efficiency improvement. And most of the time your generator is sized more closely to the load on a standby application as well. So you don't see that 10% number that we see in the rental industry. So there can be specific use cases where it makes sense, especially if there are, in your standby application, you need that peak versus continuous difference, the 3 times like I talked about. But there's not a lot of use cases for, on an economics level, where hybrid makes sense in standby. Now, if there's a sustainability piece of that, definitely it can help serve that. Especially if you're not load banking and burning that energy out in heat, and you're putting it into the battery and using it. But yeah, that's a more limited case than we see in the rental industry. Thanks for the question.